Hey, what's up, Chem peeps? Who's ready for some free response practice? You know it's always a rockin' good time. An 8.55 mole sample of methanol, CH3OH, is placed in a 15.0 liter evacuated rigid tank and heated to 327 degrees Celsius. At that temperature, all of the methanol is vaporized and some of the methanol decomposes to form carbon monoxide gas and hydrogen gas as represented in the equation below. Boom! Ooh, equilibrium. Part A. The reaction mixture contains 6.30 mole of carbon monoxide gas at equilibrium at 327 degrees Celsius. Part I. Calculate the number of moles of hydrogen gas in the tank. Alright, because we're talking about equilibrium here, I'm going to set up an ice table. Boom! Remember that when you're working with ice tables, you can use either pressures or concentrations. And in this example, because I'm given moles and volume, I'm going to convert to concentrations. So my next step is to convert my initial moles of methanol and moles of carbon monoxide at equilibrium to concentrations so that I can place them into my ice table. A quick jump to the calculator. 0.570 molar is the concentration of my methanol initially. 6.30 divided by 15. At equilibrium, the concentration of carbon monoxide gas is 0.420 molar. I'm going to plug these values into my ice table. Boom. Initially, we don't have any carbon monoxide or hydrogen gas. And as you think about the equilibrium concentration of carbon monoxide, that means that the change in concentration of carbon monoxide must have increased by 0.420 molar. And the concentration of methanol must have decreased by 0.420 molar. And be careful here, the concentration of my hydrogen must have increased by 0.840 molar. Again, remember that your change in concentration occurs based on the stoichiometry in your balanced chemical equation. So at equilibrium, the concentration of methanol remaining is 0.150 molar, and the concentration of hydrogen gas at equilibrium is 0.840 molar. Now be cautious, we're looking for number of moles of hydrogen. So now that I know the concentration of the hydrogen gas and the volume that it occupies, just a quick jump to my calculator to solve for number of moles. 0.840 times 15. At equilibrium, we're going to have 12.6 moles of hydrogen gas. Boom. Subpart II. Calculate the number of grams of methanol remaining in the tank. Well, let's take advantage of this ice table that we just created in Subpart I. We know that at equilibrium, the concentration of our methanol gas is 0.150 molar. So I'm just going to take that concentration, recognize that we're in a 15.0 liter rigid container, quick jump to the calculator to solve for number of moles. 0.150 times 15. So at equilibrium, we have 2.25 moles of methanol gas remaining in the tank. But be cautious, it's asking us for grams. Quick conversion, 1 mole of methanol has a molar mass of 32.042 grams. Quick jump to the calculator. 32.042. Our answer to 3 sig figs, 72.1 grams methanol remaining. Boom. Part 3. Calculate the mole fraction of hydrogen gas in the tank. Recognize that the mole fraction of hydrogen is equal to the number of moles of hydrogen per total moles of gas. Now, if you take a look at all the hard work that you just did in part 1 and part 2, recognize that we determined the number of moles of hydrogen to be 12.6. Boom. Total moles of gas are 12.6 moles of hydrogen plus. Oh, think about what you just did in part 2. We've got 2.25 moles of methanol remaining. Boom. And then finally, don't forget we were provided with the number of moles of carbon monoxide remaining in our tank at equilibrium originally in the problem. 6.30 moles. Boom. So our mole fraction is equal to 12.6 over 12.6. Plus 2.25 plus 6.30 21.15, which is equal to 12.6 divided by 21.15 0.596. Boom. No units required for your mole fraction. We just want to know what part of the whole is hydrogen. More than half of it. No math. Fractions. Such a great time. Subpart IV. Calculate the total pressure in atmospheres in atmospheres in the tank at 327 degrees Celsius. Oh man, I'm feeling some PivNert coming on. Boom. We're looking for our total pressure P. We know the total volume in our rigid container, 15.0 liters. Our total number of moles of gas in the container, 21.15. I'm pulling this value from what we just calculated in part III. I'm going to multiply that by the gas constant used for atmospheres, 0.0821 liters times atmospheres per mole Kelvin, times my temperature in Celsius, 327 plus 273, 600 Kelvin. Just settle in and have your good friend calculator help you out. Times 0.0821, answer, times 21.15, answer, divided by 15, answer. Total pressure in atmospheres to three significant figures, 69.5 atmospheres. Boom. So this is an example of where you can use PivNert for a mixture of gases. Just recognize that because we're using the total number of moles of gases, that the pressure we're solving for is equal to the total pressure exerted by all of those gases in that container. Part B. Consider the three gases in the tank at 327 degrees Celsius: methanol, carbon monoxide, and hydrogen. Now there are two subparts to part B. We want to know, how do the average kinetic energy of the molecules of the gases compare? And two, which gas has the highest average molecular speed? Alright, to help you better visualize this, I'm going to have a rigid container at a set temperature. And I can only put in two gases here, but you'll get the idea. The formula for kinetic energy, which is provided to you on your formula chart, is equal to, boom. Recall that temperature is a measure of kinetic energy and is dependent upon both the mass and the velocity or speed of your material. In this case, samples of gases. Because we are at the same temperature, these two gases have the same kinetic energies. So I'm going to write out Ke two times with about the same magnitude or same size. Carefully examine this simulation. The red smaller gas, so small m value, is traveling faster. Higher velocity, higher average speed. Check them out, flying around there pretty quickly. The larger blue gas is traveling more slowly. A slower velocity, a slower average speed. It's important to note that they have the same average kinetic energy because they're at the same temperature. But that does not necessarily mean that they have the same velocity, because kinetic energy dependent on both mass and velocity. The average kinetic energies are the same because all three gases are at the same temperature. Boom. Same average kinetic energy because we're at the same temperature. Brings us to subpart II. Which gas has the highest average molecular speed? Explain. Just gonna throw down this formula. So, at a given temperature, the molecules with the lowest mass have the highest average speed. Therefore, the molecules of H2 have the highest average molecular speed because H2 has the smallest molar mass. Boom! And that brings us finally to part C. The tank is cooled to 25 degrees Celsius, which is well below the boiling point of methanol. It is found that small amounts of hydrogen gas and carbon monoxide gas have dissolved in the liquid methanol. Which of the two gases would you expect to be more soluble in methanol at 25 degrees Celsius? Justify your answer. Hydrogen is nonpolar, and the only type of intermolecular forces that would exist between hydrogen and methanol would be weak London dispersion forces. Carbon monoxide is polar, and stronger London dispersion forces would exist between carbon monoxide and methanol due to carbon monoxide's greater number of electrons. Additionally, due to its polar nature, weak dipole-dipole interactions would exist between carbon monoxide and methanol. The stronger intermolecular forces between molecules of carbon monoxide and methanol indicate that carbon monoxide would be more soluble in methanol than hydrogen. Boom. Couple of important things about this last part. It's really important that when you're asked to compare things, that you always answer in terms of both substances. Do not just try to answer in terms of carbon monoxide and leave the hydrogen out. List out the structure and types of intermolecular forces for both of them in your justification. And we are done.